simplify the integral of, so we got y's, okay, 5y minus 2 over y minus 2 times y plus 6. So this is a polynomial on top, polynomial on bottom. We're being asked to integrate a rational function. Okay? When I see rational functions, the first thought is partial fractions decomposition. Okay? Something that you like. There's lots of ways to integrate, but things like partial fractions are very specific, and when you see polynomial over polynomial, your mind should immediately make the connection. Okay, basically got to be partial fractions, unless it's a very simple one that maybe we already know, like, for example, right, this one is something like it's the inverse tangent or something like that. Those are simple ones. Okay, but okay, here we go. So 5y minus 2 over, okay, so what do we do for the partial fractions decomposition? Well, first thing you would normally do is factor the denominator polynomial. We don't have to do that because somebody did that for me. For each linear factor, we introduce a new constant. And so this over here is what we call the partial fractions decomposition. What we need to do basically is just solve for a and b. All right, that's it. So what I usually do is I multiply both sides by y minus 2, y plus 6. So I just multiply both sides by the denominator. And when you do that, you'll get an a times y plus 6 plus a b times y minus 2. Now, we don't know what the constants a and b are. Hopefully they're nice. But we have one polynomial equal to another polynomial. So there's a couple strategies you can employ when it comes to solving for the constants. There's about sort of... 2 or 3 that I can think of. Probably the easiest one, if you're dealing with distinct linear factors like this, right? You don't have any repeats or anything like that, no quadratics or anything like that. So the nicest possible case. One of the easiest things to do is say, well, if these two polynomials are the same, then when I plug different values of y into this side, I should get the same output on both sides, right? When I plug it onto the right side. And so what we can do is we can do things like, hey, what would make this 0? Well, if y was equal to 2, you'd get 5 times 2 minus 2, so you'd get 8, equals a times 2 plus 6 plus b times 2 minus 2. And we chose the 2 here because 2 minus 2 is 0, so now I don't need to worry about what b is. I can see 8 is equal to 8 times a, so a is going to be 1. And we can do the same sort of trick. What makes this y plus 6 equal to 0? Well, y would be negative 6. So you plug negative 6 into both sides, and you'll get negative 32 is a times negative 6 plus 6, but that's just 0, plus b times negative 6 minus 2. So negative 32 is negative 8 times b. Divide both sides, not a. Divide both sides by negative 8, and you get b is 4. So now I've got the constants for my partial fractions decomposition. And we can go and we can actually integrate. So what we've got is 2 ways of writing the same thing. 5y minus 2 over y minus 2 y plus 6 can be rewritten as a, so y, or 1 over y minus 2 plus b over y plus 6. But we don't just want this. I mean, to find partial fractions, but we want to integrate. So we can just integrate both sides, and you actually split with the sum rule for antiderivatives, and you can actually bring this constant 4 out. And then, integrating 1 over y minus 2 or integrating 1 over y plus 6, these are things that I know how to do. I might even have a formula memorized for it. So the first one is ln absolute value y minus 2, and then we've got 4 times 1 over, the integral of 1 over y plus 6, well, that's ln y plus 6. And we add in our constant, and hey, we're all done. Not too bad.